Greetings. This is Chapter 11, Infinite Sequences and Series. We're going to discuss Section 11.10, Taylor Series. So what's a Taylor series for a function? A Taylor series is a power series, but instead of being centered at a equal to 0, we're going to allow a to be any value. So a can be 0, and you can still call it a Taylor series, but when a actually does equal 0, then you want to call it a Maclaurin series. But let's just look at the more general power series, which is the infinite sum from n equals 0 to infinity of c sub n times x minus a to the n, and we would have a radius of convergence r on that. So let's take a look at this theorem, and what does it say? It says if f has a power series representation or power series expansion at a, in other words, if f of x does equal c sub n times x minus a to the n, then its coefficients are going to be given by the formula c sub n equal to the nth derivative evaluated at a over n factorial. So let me just clarify this notation here is the nth derivative at a over n factorial. Good. And so here you can see the proof, and it's just taking a series of, pun intended, taking a series of derivatives and noting that we're going to be evaluating at a. So let's just take a look at the very first f of x. So f of x equal to the sum c sub n times x minus a to the n. If I started to write out the individual terms, this being n equal to 0, this one being n equal to 1, this one being n equal to 2, n equal to 3, n equal to 4, etc., etc. Notice here that if I were to just calculate f of a, if I calculated f of a, then c sub 0 would still be there, but this term, if x is equal to a, this would be a minus a, and that's going to be 0. So we would have c sub 0 plus 0 plus 0 plus 0 dot dot dot. And so we can tell that f of a here is just going to equal c sub 0. Now, when we go to this line, let's just take a derivative of f of x with respect to x. So if I'm going to take a derivative, c sub 0, the derivative of c sub 0 is just a constant in n, and it has no x, so the derivative of a constant is 0. But what is the derivative of c sub 1 times x minus a? A is a constant, c sub 1 is a constant, so really we're just taking the derivative of c sub 1 times x minus a, and the derivative of x minus a is 1, and so we just get 1 times c sub 1. Taking the derivative here, c sub 2 times x minus a squared, this would be 2 times c sub 2 times x minus a to the first power, then times the derivative of the inside. Taking the derivative of this term, c sub 3 times x minus a cubed, we would be taking 3 times c sub 3, and then times x minus a squared, but then times the derivative of the inside. So we do see that f prime of x does equal this long series. Now, if we calculate f prime of a by the very same reasoning that I did a few minutes ago, all of the terms of f prime of x that actually contain a factor of x minus a, if I substitute the value of a in there, then that factor becomes 0, and anything times 0 is itself, so the only thing that survives is c sub 1. And just seeing that pattern, that's 1 times c sub 1, and that actually happens to be 1 factorial times c sub 1. Now again, I'm just going to do the very same thing. I'm going to take another derivative, and I'm going to take the second derivative, and that is going to be the derivative of the first derivative. And so I begin again. The derivative of c sub 1 is 0, but now if I take the derivative of the first term, 2c sub 2 times x minus a, I get 2 times 1 times c2. When I take the derivative of 3 times c sub 3 times x minus a squared, I would get 3 times 2 times c sub 3 times x minus a to the first power. If I take the derivative of 4 times c sub 4 times x minus a cubed, I would be taking the exponent down and then subtracting 1 from that exponent, evaluating it at the inside, and then times the derivative of the inside, but that's just 1. And so you can see here that I end up with that expression for f double prime. If I evaluate f double prime at a, then all of the terms of f double prime that contain a factor of x minus a go to 0, and I'm only left with 2 times 1 times c sub 2, and that does equal 2 factorial times c sub 2. And now when we take bigger derivatives, we start introducing that derivative notation. If you ever see the exponent on f evaluated inside a parenthesis, that's how you can determine that that's the third derivative or the nth derivative of x. And in taking that third derivative, again, the first term is 0, and this derivative here would be 3 times 2 times 1 times c sub 3, and the derivative here would be 4 times 3 times 2, and dot dot dot. Every factor, if I evaluate that third derivative, and this should be 3 in here. If I evaluate that third derivative at a, I end up with 3 times 2 times 1 times c sub 3, and that's going to be 3 factorial times c sub 3. So in general, if I take the nth derivative, and this should have parentheses on the inside to determine the nth derivative evaluated at a is going to be n factorial times c sub n, and if I solve for c sub n, which is the expression for the coefficient, the Taylor coefficient, I end up with the nth derivative evaluated at a over n factorial. And then we want to take the convention that 0 factorial is equal to 1, or we just accept that fact, so that we do see that, and we also note that the 0th derivative of x is going to be no derivative, right? So we can see that this does match up, so our c sub 0 would be f of a divided by 0 factorial, and we still end up with just f of a. Good. So if our f of x does have a Taylor series expansion about a, its coefficient is going to be c sub n equal to the nth derivative evaluated at a over n factorial. All right, and we do call this a Taylor series around a, or about a, or centered at a. Okay. So for the special case of a equal to 0, we end up with a Taylor series, and we want to call that, and it's also called a Maclaurin series. So if you're ever given problems in textbooks or references to a Maclaurin series, it is understood that that Maclaurin series is a Taylor series, but that a is equal to 0, right? And you would have a c sub n times x to the n and not x minus a to the n, because a is understood to be 0. Good. All right, so if you are ever asked to find a Taylor series about a value other than a equal to 0, you cannot use the list of known power series, because the list of known power series are all Maclaurin series, and they're about a equal to 0. So if you need to find a Taylor series about any other value a, then you need to build a table and calculate individual Taylor coefficients. So here we go. In this instance, it says find the Taylor series for f of x equal to 1 over x centered at a equal to 2, and then determine its radius and interval of convergence. And I'm going to sit here and say, for the English folks out there, that's incorrect. It's not it is, it's its. So, in general, so if it's at a equal to 2, that tells me build Taylor coefficients, and I tend to build a table because then I think it's easy to keep things in order and organized. So I usually use n as my first column, And then I'll use my nth derivative. I'll calculate that one. And then I will calculate the nth derivative evaluated at f of a, and in this case, we're doing the nth derivative evaluated at 2. And then I build my c sub n, and my c sub n is going to be the nth derivative evaluated at a over n factorial. Now I tend to want to not oversimplify so that I can try to establish a pattern, because if I can establish a pattern for the c sub n's, then I might be able to, or I will be able to, put that expression for c sub n, that general expression, inside the summation notation, and I can have the entire Taylor series representation. However, if I sometimes oversimplify, I might not see that pattern, and if I do not see that pattern, and sometimes you don't, then you're going to end up writing a series of just the first couple terms and then adding plus ... to signify that you're looking at an infinite series. So here I go, calculating those values. Good. So first I'm going to say for n equal to 0, we're just calculating f of x, and we know that f of x is 1 over x, and that's x to the negative 1. I'm going to continue drawing a I'm going to continue calculating a series of derivatives, because you don't have to do everything row by row, but you can do, right? You might be able to see a pattern after this. Okay, so for n equal to 1, I'm taking the first derivative, and the first derivative here is going to be 1 times x to the minus 2. When n is equal to 2, I'm going to take a second derivative, and that's going to change it to a positive, but I'm going to still write it as 1 times 2 times x to the negative 3, because I can say that that's 2 factorial times x to the negative 3. When n is equal to 3, my third derivative is going to be negative 3 factorial times x to the negative 4. And that's usually when people start using that parenthesis notation, is on the fourth derivative. The negative times a negative turns into a positive, and when we multiply by 4, multiply 3 factorial by 4, we get 4 factorial times x to the minus 4. Good. So now I'm going to evaluate the nth derivative evaluated at a equal to 2. And so in this instance, f of 2 is going to be 1 over 2. And in this case, f prime of 2 is going to be 1 over 2 squared. And f double prime evaluated at 2 is going to be 2 factorial over 2 cubed. And f triple prime, or the third derivative evaluated at 2, is going to be negative 3 factorial over 2 to the 4th power. And the fourth derivative evaluated at 2 is going to be 4 factorial over 2 to the 4th. So now I'm going to formulate my c sub n's, and now I see that my c sub 0 is going to be my f of 2 divided by 0 factorial, which is 1/2 divided by 0 factorial. Or, and just establishing some patterns here, I'm going to go 1 over 0 factorial times 2 to the 1st power. C sub 1 is going to be the f prime evaluated at 2 over 1 factorial. And I have that this is going to be minus 1 over, over 2 squared divided by 1 factorial, which is going to be minus 1 over 1 factorial times 2 squared. C sub 2 is going to be the second derivative evaluated at 2 over 2 factorial, and I end up with 2 factorial divided by 2 cubed, but then divided by 2 factorial. And if I multiply or divide by a fraction, I multiply by the reciprocal. And I end up canceling my common factors, which is 2 factorial, and I'm ending up with 1 over 2 cubed. Good. C sub 3 is going to be the third derivative evaluated at 2 over 3 factorial, which is going to be negative 3 factorial over 2 to the fourth, but then divided by 3 factorial. Again, I'm going to take division of a fraction is multiplication by the reciprocal. And I see that I can cancel my 3 factorial, and I end up with minus 1 over 2 to the fourth. And then finally, hopefully we can establish as pattern here, the fourth derivative evaluated at 2 over 4 factorial is going to be 4 factorial divided by 2 to the fourth divided by 4 factorial, which is division is multiplication by the reciprocal, and I can cancel my 4 factorials, and I end up with 1 over 2 to the fourth. So, did I do that right? This should be 2 to the third power. Did I do that right? Third. Oh, this should be 2 to the fifth. Sorry about that. I made a mistake here. It should be 2 to the fifth power. Oh. That's going to be minus. And that's going to be minus also, or minus to 5. Oh. And this is going to be a minus as well. That's going to be a plus. Okay. All right. So this one here, and making that mistake, is 2 to the fifth. All right. So taking a look at some for pattern recognition here, I noticed that with C sub 0, I get to the 2 to the first power. With C sub 1, I get 2 to the second power. With C sub 2, I get 2 to the third power. And with C sub 3, I get 2 to the fourth power. And with C sub 4, I get 2 to the fifth power. So I at least have in my C sub n here, I at least have a 1 over 2 to the n plus 1. But now I'm looking at the positive negative. For C sub 0, I have a positive output. For C sub 1, I have a negative output. For C sub 2, I have a positive output. And then I do see that I have alternating, so I'm going to get a minus 1 to the n. But is it going to be minus 1 to the n or minus 1 to the n plus 1? If it's minus 1 to the n, that does equal minus 1 to the 0 would be a positive 1. And a minus 1 to the 1 would give me a negative, right? So I do want to multiply here by minus 1 to the n. And that's going to give me my plus minus plus minus. So since I have an n general, I can form my Taylor series. So my 1 over x, if it has a Taylor series expansion, when I start from n equals 0 to infinity, my C sub n, if I'm going to go around 2, I want to put x minus 2 to the n. And now since I have a general expression for C sub n, I can put that one in there. Good, and that is going to be my Taylor series expansion around a equal to 2 for the function 1 over x. Good. how do we find its radius and interval of convergence? Remember, we would want to do the ratio test because we have a power of 2 in there, or an exponential of 2, 2 to the n plus 1. So if I want to do ratio test to find the radius of convergence, and here we go, limit as n goes to infinity of a sub n plus 1 over a sub n is going to be the limit as n goes to infinity of, and I can remove the minus 1 to the n inside my absolute value, and I'm going to have x minus 2 to the n plus 1 over 2n plus 1, which would be 2 to the n plus 2, times the reciprocal of that, which would be 2 to the n plus 1, over x minus 2 to the n. I can start canceling my common factors. N x minus 2's cancel with n plus 1, x minus 2's to leave x minus 2 left over, and n plus 1 2's cancel with n plus 2 2's to leave one factor of 2 left over. And I have that this is going to equal my limit as n goes to infinity of x minus 2 over 2. And that is a constant under that operator, so it is going to absolute value of x minus 2 over 2. And remember, we want to force convergence, so we want to say that that is less than 1. And then I want to solve for x minus 2 absolute value, so I want to multiply by 2 on both sides. And I can say that absolute value of x minus 2 is less than 1 times 2, which is 2. And so my radius of convergence is r equal to 2. And if I want to find my initial interval of convergence, I would transform this absolute value inequality to a compound inequality, and I would add 2 to all sides, and I would end up with 0 less than x less than 4, and then I would want to test my endpoints. And in testing my endpoints for x equal to 0, I would end up with n equals 0 to infinity of minus 1 to the n times 0 minus 2, so that would be negative 2 to the n, over 2 to the n plus 1, right? If that is our function. Yep. And in doing so, then I end up with n equals 0 to infinity, and the negative 1 times negative 1 to the n is negative 1 to the 2n, right? Minus 1 to the n times minus 1 to the n is minus 1 to the 2n, and that's always going to equal 1. So we would reduce this to 2 to the n over 2 to the n plus 1. That's going to be a sum of 1/2, and and this diverges by the divergence test, because my limit of a sub n equals the limit of 1/2, and that's not equal to 0, so my series does not converge. And by the very same reasoning, x equal to 4, I am going to get n equals 0 to infinity of minus 1 to the n. 4 minus 2 is 2, over 2 to the n plus 1. That's going to give me n equals 0 to infinity of minus 1 to the n over 2. And that's also going to diverge by the divergence test, because my limit of the a sub n's is going to go to plus or minus 1/2, and that limit does not exist. And since that limit does not exist and the a sub n's are not going to 0, it diverges by the divergence test. And so my final interval of convergence is going to be open interval 0 to 4. Note that 2 is in the center of that interval of convergence. Good. So I'm going to stop here, and I'm going to continue in another video.